Okay, everyone, good afternoon. Welcome to Lecture 6 of the MSD 780 Postgraduate Dynamics course. We're going to continue today with our third study theme, which revolves around Nikravesh's body coordinate simulation program and the application examples that we want to look at using his DAP-BC algorithm that is available in MATLAB and Octave. Now, in the previous lecture, we started off with this study theme, and we first looked at two suspension examples. And this is usually a good place to start when you're looking at point-to-point forces or spring mass damper forces. A suspension system envelops a lot of the properties of point-to-point forces, the way in which we have to define the springs and the dampers, as well as some more complex joints or revolute joints, translational joints, those kind of things, how we can set them up and what their involvement is within the suspension system. We also looked then at the AA arm suspension system firstly, and this was just a basic layout of a point-to-point force with some stock standard revolute joints that we wanted to specify on the system. The McPherson suspension took it one step further, and it said, okay, if we now have translational joints in the system and we have links that have negligible masses, then we can go and look at composite joints in an effort to reduce the number of constraint equations and the number of bodies that I have in the system. Since the number of bodies and constraint equations reduce, the complexity, computational complexity of the model reduces, but I need to be aware of the fact that the mass that I'm neglecting is going to have a direct impact on the dynamics of the system. Now, in our case, for the McPherson suspension system as well, we considered a wheel that is going to make contact with the ground. In that case, we also considered the weights of the bodies. Now, I incorrectly stated in the previous lecture that for kinematics, we completely ignore the mass effect or the moment of inertia effects of the bodies when we reduce them to composite joints. This is, in fact, not true whenever we have weight acting on the system. So you'll remember that the wheel assembly actually moved downwards to make contact with the ground. The fact that it moves down is due to the weight or gravitational effects pulling the wheel assembly down. And we activated weight on all of the bodies. So that means once I start reducing the bodies, the effect or the mass and moment of inertia effect will also be felt on the kinematics of the system. It wasn't really that notable from the examples that we looked at because we had very small masses that we neglect in our composite joints. However, if you were to reduce larger masses or you ignored larger masses in the systems, then the kinematic results would have been more notable in their difference when we start reducing the number of bodies in the system. Okay, now with that being said, today we're going to look at PMD section 8.1.3, which deals with the cart example. So we're going to look at a new type of joint that we also specify in the system, which is known as a disc joint. And this is going to facilitate rolling of a wheel along some sort of a surface. Now to better illustrate this, we can refer to figure 8.9a, which represents the cart containing a main body, which is body 1, and then we have two wheels. We'll refer to wheel 2 as the rear wheel and wheel 3 as the front wheel. The wheels are modeled as discs rolling on the flat ground without slipping. A driver motor also rotates one of the wheels, causing the car to move forward. Now the individual bodies, the reference frames, and the defined points are then shown in figure 8.9b. And this is similar as what we had for the suspension systems, where we simply break up our assembly into the components and we consider the specific points on each of these bodies. So you'll see on body 1, we have points 1 and 2 defined. Its xi, eta coordinate system, local coordinate system, is also aligned with the xy global coordinate system, as well as the x or the xi, eta coordinate systems for wheel assemblies 2 and 3. On wheel assembly 2 or wheel body 2, we also have points 3 and 5, and then we have points 4 and 6 on wheel body 3 or the front wheel. Now the main objective of this example is to show how to represent a motor, either as a driver constraint or by a torque speed function. In today's lecture, we're first going to focus on cart A and B, And in this case, these will be the inverse dynamic analyses that we consider, or the case where we specify a driver constraint on the system. So where we have some sort of a known velocity, angular velocity or angular acceleration curve, and we want to obtain or measure the load characteristics of these inputs. Now moving on to Part A, if I expand this, in this model, it is assumed that the rear wheel, so body 2, rolls with a constant angular velocity of 2 pi radians per second in the clockwise direction. So in effect, this is actually minus 2 pi radians per second. To enforce this condition, we employ a relative rotation constraint as the driver, which refers to function type A for its analytical description and parameters. And we did look at function type A before, but before we apply it to our current problem, let's just look back at PMD section 7.2.8, where we looked at driver constraints. Now remember that a driver constraint can represent either a rotary motor or a linear actuator, where instead of specifying the torque or the force acted upon or acted on the body, we specify its kinematics as a known time function. And for a rotary motor acting about the axis of a pin joint between bodies I and J, as shown in figure 7.9a, a driver constraint can then be defined in the following form, where we have phi indicated in bold with a superscript dr-r, so this indicates that we're working with a driver constraint, and the r simply means that it's a rotary motor that we're considering, comma 1, and the 1 indicates that it subtracts 1 degree of freedom from the system. So a driver constraint is the same as a kinematic constraint in the sense that it subtracts the number of degrees of freedom in the system. And for both a rotary motor and a linear actuator, a single degree of freedom is then subtracted, or a single driver constraint is added to the system. Now to simply formulate this, we just say that phi is then equal to phi I minus phi j, so the relative angle between the two bodies is equal to some sort of a driver function f of t. The first and second time derivatives of this function can then simply be found by deriving with respect to t, and we then get phi dot, which is equal to phi dot I minus phi dot j is equal to f dot t. And then from an acceleration perspective, phi double dot is equal to phi double dot I minus phi double dot j minus f double dot t. And we can rewrite equation 744 in the following form, where we simply utilize the computational efficiency of the Jacobian and write our constraint equation in terms of the accelerations of the center of mass of the bodies. Now from this, it then follows that we have a Jacobian, or a driver Jacobian that is constructed for body I, a driver Jacobian for body J, and then we also have this gamma function over here, which is simply f double dot t. In our model, the body indices I and j are simply 2 and 1 respectively. So if we were to then apply DAP type A function, the general expression for this function is simply f is equal to c1 plus c2t plus c3t squared. So we are in effect defining a parabolic angular positional constraint on the system. So let's first calculate c1. So at time t equal to 0, we've defined that phi 2 at time 0 is equal to 0. We know this because if we go back to our schematic that we have over here, the xi2 coordinate axis is aligned with the x coordinate axis. So that means that phi 2's initial angle is equal to 0. And that is simply where we get that value from. Then we also note that phi 1 as a function of time is equal to 0. So the orientation of body 1 doesn't change. It isn't rotating about the z-axis. It's only going to translate along the x-axis. And looking at the driver constraint function, f of t is then equal to phi 2 minus phi 1, which is equal to 0 minus 0, and that indeed gives us 0. So if we then substitute all of the zeros into equation 8.1, it is then easy to see that c1 is equal to 0. We can now also go and calculate c3, since we know that phi double dot 2 is equal to 0 as well. And this is because we're working with a constant angular velocity. Phi double dot 1 is also equal to 0 since the orientation of the actual body of the car doesn't change. And if we look back at equation 744, we substitute that in, we end up with F double dot T, which is equal to 2C3, so therefore C3 also needs to be equal to 0. And finally, we then calculate C2. If we take the time derivative of equation 8.1, F dot T is equal to C2 plus 2C3T. But we now know that C3 is equal to 0 from the previous condition that we imposed on the system. So therefore, F dot T needs to be equal to C2. And if we look at equation 744, F dot T is equal to phi dot 2 minus phi dot 1. We know that we're working with a constant angular velocity of minus 2 pi radians per second on the rear wheel. So phi dot 2 is equal to minus 2 pi radians per second. And then phi dot 1 is equal to 0 since the orientation of the body isn't changing, which simply means that C2 is then going to be equal to minus 2 pi. And now we have values for C1, C2, and C3, and we can fully define our adapt type A function under the infunct script that we have available under DAP-BC. Okay, so from that we can then go and look at exercise 8.6 and exercise 8.7. So 8.6 says that we need to review the input M files for the card A model, and we need to note that the initial velocities are all zeros. Now if I expand over here, we're going to look also at the inanimate.m file. And before we jump into that, just to give you a breakdown of everything that we can define when it comes to the actual animation of the system. We can define additional points or outlines for improving the presentation of an animation, but what are not required for the analysis. And this we do under the inanimate. In this file, we may provide data for shape and colors of bodies, additional points for better visualization, and then also plot parameters. There is no new structure associated with this file. We use the existing structures of the bodies and points, and we simply append to them. We've already looked at an example previously where additional points anim have been specified. And we're going to look at that now again when we look at the card. So just to give you a preliminary to what we're going to look at over there. So points 5 and point 6, they don't actually connect to any joints. So therefore we can go and define them under the inanimate file instead of under the inPoints file. We only want to see what actually happens to this point as the wheels are rotating. Okay, so then we may also choose a shape out of the 3 available shapes shown in figure B9 and assign it to a body. So figure B9 shows that we can define it either as a rectangle, a circular disc, or we have some sort of a rod that is defined by its width or its height. And for any of these shapes, the program assumes that the geometric center of the shape is the origin of the xi eta frame. So the mass center coincides with the geometric center. The data for a shape is saved in additional fields in the body structure as per the explanation in table B8, and this is also then given in the DAP-BC user manual. But what you'll see is if we want to define a rectangle, the shape keyword that we use over there is RECT. Then we also give the width and the height of the rectangle. This is then shown in figure B9. Then for a circle, we also specify the shape as a circle and we give the radius of the circle. And then for lines, we can either define them in terms of their width or in terms of their height, and that will determine whether they're along the xi or the eta axes. Okay, now with regards to the program anim, the program anim displays the body mass centers and all of the defined points as small circles. The program draws lines between a mass center and every point that is defined on that body, and the assigned color to a body will be used for the lines as well, and the default color is black. Now we can specify a different color based on MATLAB's color abbreviations. The same way, in other words, when we do a plot where we specify either R, G, B, K to denote the different colors, we can do exactly the same when we define the color for the different shapes in the animation pane. All right. Now, we also want to look at section 7.2.7, which then deals with the circular disc. And this is what we're going to use to then model the two wheels of the cart that we have available. A rigid circular disc rolling on a flat surface, as shown in figure 7.8a, could represent a wheel rolling on the ground. So if I expand over here, then you'll see 7.8a is this case that we have over here, where the disc is rolling along some sort of a surface. To ensure that the disc remains in contact with the ground, a constraint such as yi minus ri equal to 0 can be implemented, where ri is simply the radius of the disc in this case. So in other words, we're simply saying that we know what the center of mass of the disc needs to be, or its y-coordinate of the center of mass, and this must be equal to the actual radius if our global coordinate system is situated on the ground surface that the wheel is rolling on. So yi should in essence be equal to ri in order for contact to occur between the wheel and the surface. Now this is then known as a simple constraint, and a simple constraint is a condition imposed on one or more coordinates of a body. For example, if the y-coordinate of a typical body I must remain equal to 0.25 meters, we write a simple constraint as yi minus 0.25 is equal to 0. And since a body has three coordinates, any of the following simple constraints can then be imposed on a body. And this is shown in 738 just for the x, y, and then the angular position of body I as well. So C1, C2, and C3 are simply constants. The velocity and acceleration constraints for these simple constraints have trivial forms, which then yield the Jacobians over here, and then we also have these gamma functions, which are all equal to 0. Now, to ensure that the disk rolls without slipping, a constraint for the no-slip condition must also be enforced. And the no-slip condition can be viewed as the relationship between the rotational and translational velocities of the disk. Now this is shown over here as minus x dot I is equal to ri times phi dot I. In very simple terms, this is simply saying that v is equal to r times omega. So the radius of the disk multiplied by the angular velocity of the wheel. But you'll notice in this case, we also have a sign that we assign just before the x dot I. And we note that when the disk rolls counterclockwise, so in other words, when we have a positive phi dot I, it translates to the left, which is a negative x dot I. So we just compensate for this sign difference by adding the negative sign in front of x dot I. The integral of this relationship then provides the position constraint for the no-slip condition as equation 7.40 that we have over here. And xi naught and phi I naught in this case are simply the initial x and phi coordinates of the disk, which we also need to give as input when we specify the disk joint in DAP-BC. The corresponding Jacobian matrix and the right-hand side of the acceleration constraints are then given in this form over here in 741. So you'll see we're working with a Jacobian of body I. We have a superscript, in this case d-ns, comma 1. So this simply means that we're working with a disk joint and the no-slip condition, comma 1. In this case, the no-slip condition removes one constraint from, or removes 1 degree of freedom from the system, so therefore adds 1 constraint to the system. Okay, and then the gamma is simply equal to 0 for the no-slip condition. Okay, so that is then just a brief overview of the circular disk. And with that, we can then move over to our DAP-BC environment over here. I'm once again in the DAP-BC 12 2022 main folder. So I'm now going to expand models, and I'm going to expand cart_A and just open up all of the input files under the cart_A model folder that we have over here. Right, so I'm first going to start with the in-bodies input folder or file. So we have 3 bodies that are defined in this case, and this corresponds with what we said in the mind map as well. We have the actual cart body, which is body 1. Body 2 is the rear wheel of the cart, and then body 3 is the front wheel. And as per usual, we just define the mass of each of these bodies, the moment of inertia of these bodies as well. We assume that these values are simply given to us. For the coordinates of the center of mass of each of these bodies, we can go and investigate it a bit closer if we look at our original schematic that we had over here for the system. Okay, so it was shown over here. Now, what is not shown in the schematic, the figure 8.9b, is that the center of mass of wheel body 2 is located 0.2 meters to the right of the coordinate system, the global coordinate system that we're working with. So with that now known, we can now go and define what the actual location of the center of mass of each of these bodies are. So if we look at body 1, its center of mass location in the x direction is then going to be 0.2 plus 0.3, which will then give us this 0.5 value that we have over here. And then if we look in the y direction, we know that the coordinate system is situated on the contact surface. So therefore, the center of mass of body 1 is simply 0.2 meters above the x-axis that we have over here. So it's 0.5, 0.2 that we specify for B1's coordinates. Then B1.P is equal to 0, so the initial angle, in other words, of the xi eta local coordinate system of body 1 is 0. And we also know this then from our exploded schematic that we have in 8.9b. We can see that xi1 is aligned with the x-axis, so therefore phi1 will be equal to 0. Then for body 2, we also specify the mass as 2 kilograms. The moment of inertia is 0.5 kilogram meter squared. And now we just need to go and find the coordinates for that wheel. In this case, wheel body 2 center of mass is then 0.2 meters away from the y-axis. So the x-coordinate is 0.2, and then the y-coordinate will be 0.1. And then lastly, for body 3, we also consider its location. So if we assume that we're working in this case with a symmetric cart, then we know it's 0.3 meters from the center of mass of body 2 to the center of mass of body 1. So from the center of mass of body 1 to the center of mass of body 3 will also be 0.3 meters. If we then look at the x-coordinate of body 3, it will be 0.2 plus 0.3 plus 0.3, which will then give us the 0.8 that we see in our script, and then 0.1 for the y-coordinate, since it's in line with the y-coordinate of body 2. Lastly, we just group all of the properties together in the bodies list over here. And once we're happy with that, we can move on to our in points folder that we have. Now, if we look at the points in this case, we have a total of 6 points, but we said that points 5 and 6 are going to be animation points. They do not connect any revolute joints or translational joints or any type of joints in the system. They are merely there to see what actually happens as the wheel is rotating. If we don't have points 5 and 6 defined, it's going to be difficult to see how the wheel is actually rotating during the animation. So we're going to leave points 5 and 6 for the inanimate input file. In our case, we're going to focus on points 1, 2, 3, and 4 when we define them in the in points file. So points 1 and 2 are specified on body 1, point 3 is specified on body 2, and point 4 is specified on body 3, and all of their local coordinates are also given in this case over here. So SP local for point 1 is minus 0.3 minus 0.1, point 2 will just be on the other side, so that would be 0.3 minus 0.1, and then points 3 and 4 are situated at the center of mass of the wheels, which is at the, well, basically at the center of the diameter of the wheels. So therefore their local coordinates are simply 0, 0. And we group all of this together in the points list at the end. Once we're happy with that, we can then move over to the revolute joints, the disc joints, and the relative rotation motor that we're going to specify on the system. So let's start fairly simple with this system. We first define the revolute joints on the system. which we first have revolute joint 1, which is going to be between points 1 and 3. Then we're going to have revolute joint 2, which is situated between points 2 and 4. And then we can go and define the disk joints. Now, if I look at this case, we can see that we have dot type, which is a revolute joint for J1. Then we have the IP and the JP indices as 1 and 3. And we have the I and JP indices for the second revolute joint as 2 and 4. So this coincides with what we saw from the schematic. Okay, now for the disk joint, we can refer back to our DAP BC user manual that we have. And you'll see under the in joints discussion, they also refer to the disk type joint that you have. And as a minimum, we need to give it an IB index as input. We need to give it the radius of the disk as input as well. And then we need to specify X0 and P0. So these X0 and P0 are simply the initial X coordinates and also the initial orientation of the disk. Now, if I look back over here, for the first disk, we can specify it on body 2. So we're starting off with the rear wheel in this case. So we specify that the disk joint is going to act on body 2. Then we give .r as input as well. So this is simply the radius of the wheel or the disk. We know that is 0.1 meters. And then we also have J3.x0. If we look back at our coordinate system, we know that the center of mass of body 2 is located 0.2 meters away from the y-axis. So therefore, x0 will be equal to 0.2. And in this case, I didn't specify p0 as equal to 0. So the default value of 0 is in any case going to be defined as 0 for J3. And then for J4, we can do exactly the same. This is now the disk joint that we specify on body 3. Then we have the radius, which is still 0.1 meters. We then have x0, which is now 0.8 meters. So this is the initial x location of this center of mass of body 3. And then we also now specify J4.p0 equal to 0. If I were to comment this out, the value of 0 would in any case be used. But for illustrative purposes, let's keep this in. Okay, and then I also need to go and define the actual relative rotation. So the motor driver that is placed on the rear wheel of this system. If I look back at my DAP BC user manual, I'll remember that for a relative rotation driver, I need to specify the two bodies between which the rotary motor is acting, as well as the function that I'm using to define the angular position. So in our case, we've defined it as a type REL-ROT to indicate that we're working with a rotational motor. IB index in this case is 2, JB index is equal to 1, and J5.ifunct is then going to be the first function index that we're going to look at. And for this, I then head over to infunct, and this is now where I define that DAP type A function. So I have F1, which is a function structure. F1.type is type A, so I need to give it as a minimum the 3 coefficients as input, C1, C2, and C3. And I know from the calculations that I did in the mind map that that is 0, minus 2 pi, and 0. I don't separate them with a semicolon in this case. I simply separate them with a space. And that is just the way in which DAP BC is going to input the coefficients. It uses a column vector instead of a row vector in this case. Or sorry, a row vector instead of a column vector. Okay, so now that that is defined, we can then just look at our in-u vectors script as well. We see that this is an open list, and that makes sense. We don't have any translational joints that we specify on the system. We only have a set of revolute joints and disk joints, so we don't expect any unit vectors. Then moving over to in-animate, this is now where we define our two animation points, so P5 and P6. We define them exactly the same as what we would under the in points folder. So it's going to be point structure, the body index, and then the local coordinates of the points. And then we group all of them together in this points underscore anim list that I have over here. Once we're done with that, we can now go and define the shapes of the different bodies just to make illustration a bit easier. So body 1 is going to be modeled as a rectangle. It's going to have a width of 0.9 meters, a height of 0.2 meters, and then I'm going to use the color red to denote the card body. For bodies 2 and 3, both of them are modeled as circles to indicate that they're disks. And then I also need to give them the R, the radius of the actual disk that is being modeled. And this is now where a difference comes in between Octave and MATLAB. When you specify bodies2.r in MATLAB, you would have just said 0.1. However, Octave uses a bit of a different modeling criteria when it sets up the radius of the circle. So in that case, you just need to actually give it 0.1 space 0.1 as the radius. So you just reiterate the radius as a second element in a row vector. And once this is done, we can then also go and define our variables pertaining to the actual animation plane itself. So the X and Y bounds that we specify over there. The X bound will be from 0 to 1.5 meters, and the Y will be from minus 0.5 to 1 meters. Once we're happy with all of that, we can then move over to our command window and we can start looking at the results. And this was then the second portion of exercise 8.6. So if I scroll down, it says that I need to execute DAP and ask the program to correct the initial conditions and then execute anim and observe the animation of the response. So to do this, I type in DAP. It asks what folder contains the model. So that would be card_A. Do I want to correct the initial conditions? Yes. And if I do this, I can see that my X and Y coordinates as well as the phi angle or orientation of the bodies match what I gave as input under the bodies input file. However, if I look at X dot, we can see that these values are no longer 0. Remember that I didn't specify an initial velocity on each of these bodies. So the default value under in bodies would have simply been 0, but because I did some initial condition correction and I have a driver constraint, which relates to the initial velocity of the system, DAP-BC was able to correct these initial conditions, and these are now the actual X dot values that I get, or the initial velocities of the system that I get out. And in addition to this, Y dot is 0. This we don't expect any of the bodies to actually move up or down. We simply expect them to translate then from left to right if we have some sort of a clockwise angular velocity being applied on the rear wheel. And then finally, phi dot, you'll also see for bodies 2 and 3. If you go and relate this minus 6.2832 to the radians values, this will simply be equal to minus 2 pi radians. So this is exactly what we gave as input as a driver constraint to the system. Constant angular velocity of minus 2 pi radians per second, and DAP-BC was able to correct accordingly. Now, for the final time, I'm going to use a 1 second final time over here. So if we use minus 2 pi radians per second constant angular velocity, after 1 second, each wheel will have made a single revolution. Then for the reporting time step, I can use a 0.01 second reporting time step. It runs for 69 function evaluations, and then I can just type in anim and see what actually happens to the system. So if I hit any button over here and I make this larger, we can see that indeed the cart is moving from left to right as the wheels are moving at an angular velocity of minus 2 pi radians per second. So the wheels are indeed rotating clockwise during this process as well. Okay, and after 1 second, we can now also see that that starting line that we had now made one full revolution on body 2 and 3. So indeed, after 1 second, we have a full revolution, and that coincides with what we expect from the system for a minus 2 pi radians per second angular velocity. Okay, so that was then exercise 8.6. Exercise 8.7 then says that we need to execute that, but now we're not going to ask the program to correct the initial conditions. And we want to keep all the initial velocities at 0. We didn't specify them, so the default of 0 is in any case going to be used. Then we need to perform an animation of the response, and we want to see what we observe in this case. Now, if I go back over here, I'm simply going to type in clear all, close all CLC, just to clear my workspace. I'm going to type in DAP again, cart_A, and now, no, I don't want to correct the initial conditions. My first warning that I see over here is that there are redundancy in the constraints. So in other words, from this warning, I don't really expect my system to move as it should, given the input constraints that I give. Okay, I'm once again going to use a final time of 1 second, but let's perhaps use a bit of a coarser time step this time. So let's do 0.1 seconds, just to make it a bit easier to visualize or quicker to visualize. If I type in anim, I can see that all of the connections seem to be correct, but let's see what happens when I actually run the animation for some sort of a time. Okay, so in this case, we can see that nothing is happening. The system is remaining stationary. We don't see that the cart is moving from left to right. And our animation has also now terminated. So what would be the reason behind this? Well, if we look at the solution, we observe that nothing moves, even though we have a driver stating that the angular velocity of body 2 is minus 2 pi radians per second. The reason is that when we solve the equations of motion, we only enforce the second time derivative of the constraints, including the driver constraint. Referring back to lecture 4, where we listed the position constraints in equation 1319, the velocity constraints, the acceleration constraints, and the equations of motion, we grouped all of them together in 1319 to 1322. And the second derivative of our driver constraint enforces that phi double dot 2 is equal to 0. So if we start the simulation with a 0 angular velocity, the driver acceleration phi double dot 2 is equal to 0 will keep the velocities unchanged at 0. So it doesn't worry about whether it's satisfying the angular velocity constraint that I specify on the system, but rather the angular acceleration constraint that I specify. Since the system starts at 0 velocity, it's not allowed to have an angular acceleration. So the system simply says that, okay, in that case, I'm just going to remain at rest, and I will in any case be able to satisfy all of the constraints. All right, so before I then move on to card B, are there any questions at this point? Okay, I don't see anything under the chat messages. So in that case, we can then move on to card B. So card B is still going to consider the inverse dynamics of the system. We're still going to specify a driver constraint on the system, but instead of now looking at a type A function, we're going to focus on what we call a type C function. And once we've expanded this section, I can show you what that looks like. All right. So this model is the same as the model card A, except for the driver function now referring to function C instead of A. If we go to our DAP BC user manual, we can look at what a DAP type C function looks like. And the first derivative of this function rises from 0 to a final value during a specified time period and keeps that value for the remaining duration of the simulation. This function can be useful in simulations where a driver should raise the velocity or the first derivative from 0 to some sort of a specified speed. And that we can see from this second graph that we have over here in figure B8. So we start at 0, but after some time t end, we have reached some final velocity or some final speed in the system. The general expression for this function is then given as equation 8.3, where we have f equal to c1 plus c2t to the fourth plus c3t to the fifth plus c4t to the sixth. So we have quite aggressive polynomials or high order polynomials in this case that we need to use, but all of them work together to ensure that we can meet all of these figures in B8. So the function has a 0 first, second, and third derivative at the start. This we can see as 0, 0, and 0 for df dt, d square f over dt square, and then d3f over dt3 as well. And then the function also has a 0, second, and third derivative at the end. Right, so not for the df dt, but for d square f over dt square and d3f over dt3, we can see that at t end, both of those values are indeed 0. Now the first derivative has a non-zero value at the end point. Okay, and that we know from the fact that we want to raise the velocity from 0 to some sort of a specified speed. So since the specified speed will be non-zero, df dt at the end will also need to be non-zero. And the user must then supply 4 parameters as input to the dap type C function. The start and end values for t, so t start and t end. If t start isn't specified, then the standard of 0 is in any case used over there, but t end does need to be specified. Then we also have the start value for f start. Once again, if this value isn't specified, then the default of 0 is used. And finally, the end value for the first derivative. So df dt max, which is equal to df dt underscore end, when we provide it as input to DAP-BC. And the program DAP then computes the 4 coefficients of equation 8.3 and enforces the driver constraint accordingly. So now for card B, the angular velocity of body 2 needs to start from 0 and reach the desired speed of minus 2 pi radians per second. So now we no longer have a constant angular velocity, we have an angular velocity that is increasing over some sort of a time period. So this already tells me that I need to use a different type of DAP function when specifying the constraint equation. So therefore, we need to specify the 4 parameters as follows. We first specify t start as 0, which is in any case the default, so that's fine. We specify t end as 2 seconds, and this we simply get from the equation or the summary that is given over here. F start is then also defined as 0 because we need to raise the velocity from 0 to the desired speed of minus 2 pi, but we know that initially our function is also going to start at 0 because our initial orientation of body 2 is 0. And finally, df dt end is then the first derivative, so in other words, the angular velocity that we're looking at for the function, and that is the minus 2 pi radians per second, which is also given over here. The program DAP will then compute the 4 coefficients, and the first derivative of function c will then look as shown over here in figure 8.10. So we have phi dot 2, which is in radians per second, time, which is in seconds. So over 2 seconds, we can see that the angular velocity decreases from 0 to minus 2 pi radians per second. This minus 2 pi is simply this minus 6.28 radians per second that we had previously as well. Okay, so now of course the question would also be what happens beyond 2 seconds. So if we were to run the animation from 2 to 3 seconds, in that case, DAP-BC is simply going to assume that it has now reached a constant angular velocity. So from 2 to 3 seconds, the angular velocity of the system will then remain at minus 2 pi radians per second. And we're going to look at that as well when we run the post-processing of this example. And on that note, we can then also look at exercise 8.8. It says that we need to review the input M files for this model. We need to execute DAP and then execute anim and observe the animation of the response. And we can then execute post and plot the angular velocity of body 2 versus time. and the plot should reveal that the angular velocity has been varied from 0 to the final value in the described time period as depicted in figure 8.10. So 8.10 was this figure over here. Right, so with that in mind, let's first review the DAP-M files. So I'm first going to close all of the card A input files that I have over here. And then I can go to card_B. If I expand it, I can just open all of its input files as well. Okay, so in bodies remained exactly the same as what we had for card A, nothing changed over there. In points will also remain the same. We still have 4 points that we use to construct our joints. In joints remains the same as well. So we have 2 revolute joints, 2 disk joints, and a relative rotation driver that we specify on the system. The actual joint definition itself hasn't changed, but the function itself is now going to change. So if I go to infunct, you'll see previously where I had function type A, I now specify function type C. And there's only 2 non-zero inputs that I need to give in this case, T-end and df_dt_end. Since all of the other inputs are 0, I can just use their default values and I don't have to specify them. So T-end is 2 seconds, df_dt_end is then minus 2 pi radians per second. And then I also have, I think, in forces is simply the weight acting on the system, the same as for card A. In U vectors is still going to be an open list in this case. We don't have any translational drivers on the system, or translational joints on the system, so that's fine. And in animate also remains the same as for card A, where we specify our 2 animation points, 5 and 6, and we specify the shapes and colors of the bodies. So the card body and the 2 wheels or discs that we're modeling. And now the only difference that we have over here is the bounding box for our animation pane has now increased from 0 to 2.5 meters. Y min, I think, remained the same from minus 0.5 to 1 meters, so that's fine. Okay, so with all of that then being said, we can execute DAP. Now our model that we're considering is card_B. Do I want to create the initial conditions? Yes. And in this case, after initial condition correction, I can see that all of my initial velocities are 0, and this is in line with the new specification that I have on the angular velocity. It starts at 0, and it then decreases to minus 2 pi radians per second. So that is fine that I have an initial velocity of 0 for all of the bodies. Then for the final time, I can now do 3 seconds. So I'm going to go beyond the 2-second threshold that was specified and see what happens to the actual angular velocity in this case. And the reporting time step, I'm going to use an 0.1 second time step just to make the animation a bit faster. If I type in anim, I can see that all of the systems are well connected. So I can now go and run the actual dynamic simulation. If I increase this, we can see that the card is starting to move from left to right, and with each increment that is being plotted or each animation frame, we can see that that line is starting to accelerate more and more. So we do see some sort of an acceleration in the system. Okay, so the animation is fine. To now plot it a bit more accurately, I'm just going to clear my workspace again, rerun DAP, and I'm just going to use a finer reporting time step in this case. So I'm still running card B, still going to correct the initial conditions, plot it over 3 seconds, and now I'm going to use a let's perhaps do a 0.005 second time step over here. Okay, now it says that I need to execute post and plot the angular velocity of body 2 and see if it coincides with what I get in figure 8.10. So to do this, I'm just going to type in post over here. And now I can start plotting. So to plot, I'm just going to type in plot. I'm going to use on the x-axis the time variable, so t. And now since I'm interested in the angular velocity, I'm going to scroll down and I'm actually going to use PD in this case. So we have PD, which is a 601 by 3 dimension, so the number of time steps by the number of bodies. So I type in PD. I'm going to plot it for all time steps, so I'm going to use a colon in the first argument. The second argument will then be the body that I'm specifying, so it's on body 2 that I want to specify the angular velocity. So I can just type 2, close the 2 brackets, and then I can plot the results over here. Okay, and what you'll see is that we do indeed start from 0 radians per second. We decrease our angular velocity to minus 2 pi radians per second, or minus 6.28 radians per second. And then from 2 to 3 seconds, that BC assumes that we're now working with a constant angular velocity. So from 2 to 3 seconds, we just have a constant line that remains at minus 2 pi radians per second. So this indeed correlates well with figure 8.10 that I have over here. Okay, so before I move on to the reaction forces, where we're now going to start looking at the dynamics of the system and looking a bit more closely at the Jacobian, are there any questions from the kinematics at this stage? Okay, I don't see any questions, so I think we're still fine on that front. Okay, so now we can jump into looking at plotting the torque associated with the prescribed rotation of the rear wheel. Remember that we now specified a relative rotation driver on the system. Its corresponding Lagrange multiplier is therefore a reaction torque that is being applied on body 2. We also want to look at the reaction forces on the rear driver wheel and the front driven wheel. Now the reaction forces can either be due to the revolute joints or the actual disc joint that is specified on the system. Remember that we have, for a disc, we have some sort of a contact force or a normal force that is acting upward on the disc. And then we also have the no-slip condition, which is acting in line with the line of translation between the disc and the contact surface area. Now, to better describe this, we can go back to reaction forces in PMD section 4.4.2. Reaction forces, or torques, act between two bodies along or about the axis for which no relative motion is allowed. A kinematic joint, we now know, removes one or more of the 3 relative degrees of freedom between two planar bodies. The imposed restrictions on the relative motion expressed analytically are then called constraints. And we can consider the two bodies that are connected by a pin joint or a revolute joint or a hinge joint, and these are shown in figure 4.10a. So a pin joint allows the bodies to rotate relative to one another, but it eliminates the relative translation between the attachment points along any two orthogonal axes. And usually it's customary to use the global XY frame as the orthogonal axes. Since it's removing the translation between the two bodies, we need to compensate for it by 2 reaction forces when we break up our assembly of bodies I and J. And since this joint removes 2 relative translation degrees of freedom, the resultant reaction force on each body can then be described with 2 Lagrange multipliers, which are shown as lambda 1 and lambda 2. And they are then shown in this case on body I and J. They're going to have the same magnitude but act in opposite directions. Now for a circular disk, the circular disk may roll against the flat surface of another object as shown in figure 4.10g. So we have body I, which is the disk, and body J, which is then a translational body at the bottom. And in this case, if we then look at the reaction forces, we also have a normal reaction force or a contact reaction force, which is lambda 1, and lambda 2, which is then a no-slip condition force that we specify on the system. So the fact that the two bodies remain in contact means that there has to be that reaction force lambda 1 perpendicular to the line of contact. Furthermore, if no slippage is allowed between the two bodies, another degree of freedom is removed, and this condition necessitates a second component of reaction force, lambda 2, that must also be considered. For the constraint formulation, the constraint equations of motion, including all the kinematic constraints, are then expressed in 1319 to 1322. And to solve equation 1322 for the accelerations, we simply append it to the acceleration constraints of 1321 to form the following set of equations. And this should look familiar from one of our initial lectures on the mathematical model that is used in DAP-BC. So with regards to PMD sections 13.6, we also consider a combined analysis where we assume that there are NV coordinates and NC independent constraints for a multi-body mechanism. So therefore, the number of degrees of freedom that we have in the system is equal to NV minus NC. And remember that NV is simply the number of bodies multiplied by 3, since each body has 3 free degrees of freedom, which is in the x direction, y direction, and about the z axis. So the NV equations of motion and NC acceleration constraints based on equation 1323 are then expressed in 1361 as well. And we can now assume that we include ND driver constraints, which we can express simply as phi superscript dr, which indicates that we're working with driver constraints, which is a function of q and is then equal to f of t. Now remember, for equation 1361 up to now, we haven't considered the driver constraint. We only consider the constraint equations that are facilitated by kinematic joints, so actual connections between the bodies. For driver constraint, we enforce some sort of an angular velocity or angular acceleration or a linear velocity or acceleration on a system. So that is not an actual kinematic joint acting on the system. It's an input that we give to the system, an externally applied driver motor on the system. But we need to be able to compensate for that in a similar fashion as to 1361. Now the time derivative of the driver constraints are then simply expressed as f dot t, which is equal to the Jacobian, the driver Jacobian, multiplied by q dot, which is the velocity vector. If we go one step further, we can find the second time derivative, which relates to the accelerations and the velocities. And this is simply facilitated by the product rule. So f double dot t is then equal to the derivative of the driver Jacobian multiplied by q dot plus the driver Jacobian multiplied by the acceleration vector q double dot. The second time derivative of the driver constraints can then be rearranged so that we have this form over here in 1362. And finally, we can then include these driver constraints as an addendum to 1361. So 1361 simply becomes 1363, where we then have our last row our last row matrix, which corresponds to the driver Jacobian and the driver reaction forces in the system. If we then isolate the equations of motion from equation 1363, this yields this mq double dot equal to d prime, so the constraint Jacobian, the transpose of the constraint Jacobian multiplied by the reaction forces of the kinematic joints, plus then we have the transpose of the driver Jacobian multiplied by lambda plus h. And these first, or the Jacobian multiplied by the reaction force is now the important aspect that we're going to focus on when we start looking at the reaction forces now in the system. Remember, up to now, we've considered revolute joints, and we said that usually we're just interested in the magnitude. But if you are interested in the actual sign and the actual impact that the reaction force has in the system, when you consider more complex joints, you need to also multiply it by its element within the Jacobian. But just take note that there's going to be some multiplication that we're going to do between the Jacobian and the Lagrange multiplier to extract that specific reaction force. Okay, so with that being said, we can then jump directly into the system Jacobian and how it's set up in DAP-BC. Now, the Jacobian matrix for a multi-body system is constructed from the Jacobian submatrices of its joints. In this subsection, we use a simple example to show the process of constructing the Jacobian matrix in its generic form. If I expand this point once again, we can then consider the generic multi-body system in figure 7.10. So this is a simple slider crank mechanism that we have over here, which consists of 3 moving bodies. So bodies 1, 2, and 3. Body 1 is simply a crank link that we have. Body 3 is then a sliding rod, and body 2 is some sort of a sleeve in which body 3 is sliding through. Now, with regards to this, the system also contains 3 pin joints and 1 sliding joint, which yield 8 algebraic constraints, so 2 per joint. Remember that revolute joints remove 2 constraints, which is the x and the y, or the translation of the system, so the x and y translation, but it does allow rotation. So there are 2 constraints removed per revolute, or 2 constraints imposed per revolute joint. And then for a translational joint or sliding joint, it removes rotation between the 2 bodies and translation in one of the directions. So that one also removes 2 degrees of freedom from the system, and therefore enforces 2 constraints in the system. And that's how we get 2 times 4, 2 constraints times 4 joints, which gives us the 8 algebraic constraints. For the moment, let me just go back. For the moment, let us assume that the ground, body 0, is also a moving body. Therefore, we have 12 coordinates, so 3 per body, and the system Jacobian should then be an 8 by 12 matrix that we construct. So the number of rows matches the number of algebraic constraints that we have, and the number of columns matches the number of coordinates that I have in the system. Now, we can also assume that the joint constraints are assembled in the following order. So A, B, T, and C, which simply means that we first define revolute joint A, then we define revolute joint B, then we define the translational joint or the sliding joint T, and finally we define revolute joint C. And the order of this is important when we consider the actual Jacobian and where all of the constraints are placed within the Jacobian matrix. Now, the Jacobian matrix for the pin joint A between bodies 0 and 1 can then be obtained as 2 2x3 submatrices from equation 7.17. If I expand over here, you'll remember that 7.17 considered the Jacobian of the system. So we have the Jacobian for body I, the Jacobian for body J, and then we multiply this with our acceleration or our combined acceleration vector for bodies I and J, plus then we have some sort of what we consider a multiplication with the actual velocity vector of the system. And we can simply go and rewrite this in this compact form in 7.17 as well. Once again, just to understand, if we talk about SIP and minus SJP with this little concave sign above it, it means that we're talking about the rotated vector. And we discussed this in one of our previous lectures as well. If we have some vector A and we rotate it 90 degrees counterclockwise, we end up with A rotated and its new components as well. And this is then applied to the Jacobian matrices as well. Now, these submatrices, denoted by D0A and D1A, occupy the top 2 rows and the left 6 columns of the overall 8 by 12 Jacobian matrix. Now, similar to this, the submatrices for other joints are also placed in their corresponding rows and columns to form the following matrix. And you'll notice D0A, D1A, all of these are bold. So they actually indicate submatrices that we are working with. And we can now investigate, well, what does this mean when we construct the actual joints between the systems? Well, if we look at joint A, which we said is the first joint that we specify, we know that joint A is acting between bodies 0 and 1. So when I specify its Jacobian properties, it needs to correspond to the columns for bodies 0 and 1, and also the first row, or the first set of rows that correspond to the constraints of the revolute joint. So what does this mean? This means that when I have bodies 0, 1, 2, and 3, which are shown here as the different columns, then I also have revolute joint A as row 1, revolute joint B as row 2, the translational joint as row 3, and then row 4 will be revolute joint C. So we know that we're working with revolute joint A, so that means we need to work in this first row that we have over here. It's acting between body 0 and 1, so its Jacobians will be constructed in column 1 and column 2, which corresponds to body 0 and body 1. In a similar fashion, we can look at revolute joint B. So revolute joint B is placed between bodies 1 and 2, and it's also the second revolute joint, or the second joint that I specify, so it's in the second row, acting between bodies 1 and body 2. So I place it in the second and the third column. For the translational joint, if I go up, translational joint acts between bodies 2 and 3, and it's also the third joint that I specify, so I'm going to row 3, and I consider it working on body 2 and 3, so body 2 and body 3's Jacobians will be populated in these elements over here. And then finally, revolute joint C is constructed between ground and body 3, so that means my final constraint, which is the last row that I have over here, acts between body 0 and body 3, and that is where I'm going to place their Jacobians. Now in this matrix, each generic row represents 2 actual rows, and each generic column represents 3 actual columns. The blanks simply represent 0 entries. Note that a sliding joint and a pin joint have the same generic form, so both of them are 2 by 3 submatrices that I enforce on the system. Now so far, we have considered body 0 as a moving body in order to make the process of constructing the overall Jacobian matrix more easily understood. But since body 0 is a non-moving body, so its velocities and accelerations are always 0, we can remove its corresponding columns from the Jacobian matrix, and this then yields an 8 by 9 system Jacobian matrix, which is shown in this case over here. So we simply remove this first column that we have. If the process of constructing the overall Jacobian matrix is then well understood, there will be no need to first include the ground as a moving body and then remove its corresponding columns. We can directly define the Jacobian matrix in its final form. Okay, so it was a bit vague considering the submatrices that we have to set up. So let's perhaps consider the Jacobian matrix in its entirety for our card B simulation that we are considering. Now, what I want to focus on for the Jacobian that we're going to set up for card B is we're not too interested in this minus eta 1 P1 values and what they actually mean when we set up the original Jacobian. We just need to understand that there are non-zero entries and what the non-zero entries refer to when we set up our different constraints. Now, before we start with this, we first need to consider the order in which we actually defined our joints in card B. So if I go back to in joints, you'll see I defined J1, J2, J3, J4, J5. So they are specified in the same order as what I have in the context of this file over here. So I first define the revolute joint that acts between points 1 and 3. So the revolute joint between body 1 and 2. Then I specify the revolute joint between body 1 and 3, so between the card body and the front wheel. Then I specify the 2 disc joints. So first the disc joint on the rear wheel, then the disc joint on the front wheel. And after I've done all of that, now I go and define the motor driver in the system. And the motor driver is going to remove a single degree of freedom from the system, so it imposes a single constraint in the system. Now, if I look at the form, I know that a revolute joint also removes 2 constraints, so that means I'm going to end up with a Jacobian that is 2 plus 2 plus a disc joint, which also removes 2 constraints, so it's 2, 4, 6, 8, plus the final motor driver constraint, which is in plus 1. So I'm going to have 9 rows in the Jacobian matrix. How many bodies do I have in the system? Well, I have 3 bodies. I have the card body, which is body 1. Then I have body 2, which is the rear wheel, and body 3, which is the front wheel. Each of them have 3 coordinates, so it's going to be 3 times 3, which is equal to 9. So I'm going to have 9 rows and 9 columns when I construct my Jacobian. Okay, and this is indeed what I end up with in this case for the Jacobian that was constructed over here. Now, what you'll notice is that the Jacobian matrix is also broken up into three blocks that we have. So column blocks, basically. Block 1 refers to body 1. Block 2 is then body 2. And block 3 is body 3. And each of them then have an X, Y component, and then also rotation about the Z component. Okay, and they're all X, Y, Z, X, Y, Z. Then for the number of rows that I have, I can count over here. I do indeed have 1, 2, 3, 4, 5, 6, 7, 8, 9, with the final row being the driver constraint that I specify on the system. Okay, so from this, I can also see that whenever I specify a revolute joint on a system, the reaction forces that are constructed, remember that a revolute joint, the first revolute joint that I have is between bodies 1 and 2. So I go to body 1's block and body 2's block, and I populate their Jacobian values in over here. What you'll notice, however, is that in the first row, I have an X value which is non-zero, the Y value is 0, and then the Z value is some rotational component that I'm not really considering when I consider the reaction forces. But then the second row, I have a 0 in X, but a 1 in Y. So this tells me that I first extract the X reaction force, then I extract the Y reaction force if I use the Jacobian. The same then for the second revolute joint, which is constructed between bodies 1 and 3. I first have the X reaction force, which is considered, then the Y reaction force. For the disk joints, this turns around. I first have a Y reaction force, which is the normal force or the contact force of the disk that I consider. And then I have some sort of an X force in this case, which considers the no slip condition. For the second disk that I specify, which is on body 3, in this case, I also first have the contact force and then the no slip force. And finally, for the relative rotation driver that I specify on the system, you'll remember that a relative rotation driver equates to a torque load or torque reaction that is placed on the system. So therefore, if I look at the components over here, I have X, Y, Z, which is the non-zero, and there I have a -1 or a 1. And that relative rotation driver also acts between bodies 1 and 2, and that's why the blocks of body 1 and 2 are populated over here for the final row. Okay, so what does this mean when I want to go and consider the reaction forces? So if, for example, I want to consider the torque, the driver torque that is specified or that is executed on body 1, then I can say, well, I want to then use in the Jacobian matrix the final row for body 1. So that would be row 9, column 3 is the Jacobian entity or element that I'm interested in, and I can use this value and multiply it by the Lagrange multiplier, which is then also the 9th element in the Lagrange multiplier, and that will then give me the correct sign and the correct magnitude of the driver torque that is acting on body 1. For body 2, it will just be, in this case, row 9, column 6 that I'm going to extract the Jacobian for. Okay, now this is perhaps better illustrated also when we consider plotting the torque associated with the prescribed rotation of the rear wheel. Now, if I expand this, you'll see that it says the torque associated with the prescribed rotation of the rear wheel. So since we're working with the prescribed rotation, it means that we consider the driver constraint. If I then go back to this list that I have over here, I still have the results from the Card B kinematic analysis and the dynamic analysis that I ran, so I can simply continue working with this. I'm now just going to say, well, I want to consider torque 2, which is then equal to the Jacobian, and let's perhaps just first consider the very first element. So at time step 1, I'm just going to say Jacobian 1, and if I look at the form, the Jacobian has the form the number of time steps by the number of constraints by the number of coordinates in the system. So the constraint that I'm considering is the very last constraint, which is the driver constraint. So it's going to be row 9, and then the body that I am interested in is body 2. So if I look at the Jacobian, it's body 2, so I'm working in the second block over here. We know that the relative rotation driver is in the z-axis, so it's going to be column 6 that I'm going to use. And I'm simply going to type in over here 6, hit enter. Sorry, I shouldn't have called this torque 2. This is actually just the Jacobian that I'm now extracting. But we can see the Jacobian in this case is 1. And this corresponds to what we had in the mind map as well. This entity is 1. But now to get the actual reaction force, or the reaction torque in this case, I'm just going to say it's actually torque 2, which is equal to Jacobian. I'm going to consider it for all of the time steps. It's still going to be constraint 9 that I consider, and coordinate number 6. And then I'm going to type dot star, so that just means I'm using element-wise multiplication. And I'm going to multiply this with the corresponding Lagrange multipliers, which are the reaction forces without their adjusted signage. For all of the time steps, once again, comma, and now I just need to remind myself that for a Lagrange multiplier, I'm working with 601 by 9, so that is the number of time steps by the number of constraints that I have. I'm considering constraint 9 again, so I simply type in 9 over here. And if you want to just double check your method as well, you can just make sure that the second element of the Jacobian always matches the second element that I specify for the Lagrange multiplier. So both of them are 9 in this case, so that's fine. I can hit enter, and now it calculated torque 2 in the background, and now I can simply go and plot this versus time. So I'm just going to say plot t on the x-axis, and let's do torque 2 on the y-axis. If I hit enter, then this is the result that I get. So the torque on body 2 starts at 0. It reaches a minimum peak over here. Then it goes back to 0 after 2 seconds, and that is where I no longer have angular acceleration in the system, or no acceleration in the system, and that's why I then have a 0 torque from 2 to 3 seconds. So this corresponds well with what I expect for my input driver constraint. If I compare this then also to the results that I have available over here, let me just go down. We can see that this indeed matches what I have in the mind map, so that's fine. And the multiplier associated with the driver constraint is then also shown in figure 8.11a, which is the torque in this case. So the Lagrange multiplier matches the torque of the driver constraint. Okay, so next up, and perhaps before I expand that, we can also go and plot the reaction forces associated with the no-slip constraints of the rear and the front wheels, so body 2 and body 3. And we can plot them on the same graph. Yeah, we can plot them on the same graph. That shouldn't be an issue. But we just need to understand once again where we're going to extract the Jacobians from. So since we are interested in the no-slip condition, we know that we're working with the 2 disc joints. The no-slip condition is also in the x direction in this case, since that is the direction along which the disc is rotating, or so the direction along which the disc is translating perhaps. If I look back at my Jacobian that I constructed for card B, we can see that for the no-slip condition, I'm interested in the x values for body 2 and body 3, so for the front, or for the rear and the front wheel respectively. And I'm going to then use this component over here, which correlates to the x. So if I count the number of rows, that's 1, 2, 3, 4, 5, 6. So row 6, column 4 will be the Jacobian element that I have to multiply with its Lagrange multiplier to get the correct reaction force. And then for body 3, that would be row 8, column 7 that I'm going to use over there. And that will then give me the no-slip reaction force on body 3, or the front wheel. Now, to do this, I'm just going to call the no-slip condition on body 2 no-slip 2. And this will be equal to the Jacobian for all time steps. I said I'm considering, in this case, row 6, column 4. So I'm just going to type 6, 4. And then I just dot multiply it with the Lagrange multiplier for all its time steps. And I know that the second element needs to match, so I'm considering constraint 6. And then I calculated no-slip 2. So for no-slip 3, it's once again going to be the Jacobian for all the time steps. I'm interested in the no-slip condition, so it's the x direction. It's going to be row 8, column 7. So I'm simply going to type in 8, 7, dot multiply with Lagrange. I make sure that the second element of the Jacobian matches the second element of the Lagrange, so it's going to be 8. If I'm happy with that, I can then simply go and plot these results. So I'm first going to say plot t no-slip 2, and let's do a blue line for this. And then I can also plot t no-slip 3, and let's use a red dashed line to indicate this. And then if I hit enter, then these are the resultant no-slip conditions on the rear and the front wheel, with the rear wheel being indicated in a blue line and the front wheel being indicated in a red dashed line. All right, and I can also go and compare this then to the results that I have in the mind map and also then in the PMD textbook, figure 811b, and it seems to correlate well. And what we note from this is that the reaction force on the rear wheel is positive, since this is the driver wheel, but for the driven wheel at the front, it is negative. Okay, so that is then the implementation of the reaction forces and the correct signage associated with the reaction forces based on the actual Jacobian matrix as well. Whenever we do these type of reaction forces, we need to consider the Jacobian and the Lagrange multiplier matrices in tandem with one another. Make sure that we extract the correct elements so that we can get the correct signage and the correct magnitudes or multipliers as well. Okay, and that is then also the end of the card B example that we wanted to look at. Yeah, so I think before I then end off our inverse dynamic analysis of the card, are there any last questions? All right, so if you are busy typing a question, perhaps just in the meantime, with regards to the MSD 780 assignment 1, it should be posted at the start of September. So if I quickly look at the calendar over here, I think by next week's lecture that we have, which is the 4th of September, the first assignment for MSD 780 will be posted, and its due date will be, I think, at the end of the first week of October. So let's just see when that is. Yeah, so I think we can make it the 8th of October, which will be the deadline for assignment 1. Perhaps just to give you a bit of a breakdown of what you can expect from assignment 1, it will be constructing your own multi-body mechanical system. Of course, there has to be some complexity in the system. So instead of just relying on a bunch of revolute joints and very simple joints in the system, I do want to see some complexity when you construct the mechanism. But it's going to be constructing your own mechanism, multi-body mechanism, and then performing a dynamic analysis on the system. So a kinematic analysis and then a dynamic analysis on the system, and also giving a proper breakdown of the results that you got, and also perhaps doing some validation on the calculations as well. So perhaps using something like your initial conditions to see, well, are the forces that I get from DAP BC in accordance with what I do when I do a quick hand calculation. So yeah, basically to summarize, you're going to do your own mechanical system, a kinematic analysis, a dynamic analysis, and a validation on the system. And that will then be assignment 1. I'm going to give you, I think now, a bit more than a month to do the assignment as well. So that should also cover you with regards to our upcoming application examples. So if you're not sure about anything, the application examples will also guide you on how you can go about setting up your own mechanical system. But it should be sufficient time for you to engage with the assignment and understand the underlying principles that we applied up to now. Okay, but with that being said, I see there are no other questions, so then I'm going to end it here for the night, and thank you very much. I'll then see you in lecture 7 next week. Thank you.